everyone. So today we are going to deal with thermodynamics and kinetic theory of gases in one take. So let's see the essential theoretical concepts quickly, and then we will see the explanation of various concepts through different types of questions. Okay. So as you saw that the chapter has been divided into two parts, thermodynamics law and as well as kinetic theory of gases. So first we start with kinetic theory of gases. In short, I am writing it as KTG. So it has been proposed by Maxwell, and this is for ideal gases only. So this thing should be clear to everyone, given by Maxwell. Now in ideal gases, the kinetic gas equation and the ideal gas equation, which is to be obeyed by all the ideal gases, PV is equals to nRT, where N is the number of moles, T is the temperature, R is the gas constant, whose value when you are solving questions, do take it as 25/3. It will make your calculations easy. Joule per mole per Kelvin. Temperature obviously is in Kelvin. PV is equals to nRT, and when we use Maxwell's kinetic gas theory, then we get PV also equals 1/3 m total V RMS square, where m total is the total mass of gas, which is mass of one molecule multiplied by number of molecules. So this m is mass of one molecule, n is the total number of molecule. So this V RMS is our RMS speed, root mean square speed, and from this relation we know number of moles is the total mass by molecular mass or molecular weight. So from here VRMS expression is obtained in two forms, whichever you can use in question: root 3 P by rho, because volume is also written as total mass by density. So either you write in this form or you write root 3 RT by molecular weight, or you can put another constant, because molecular weight is mass of one molecule into Avogadro's number. So using that concept, we can express it in one more important form: root 3 kBT by m, small m. Small m, as I told, is the mass of one molecule, and T is the temperature. Kb here is the Boltzmann's constant. Now for this also students struggle to remember its value. Simply remember Kb, Boltzmann's constant, is R by Avogadro's number. When you are using R, use 25/3, and Avogadro's number for questions directly use 6 into 10 to the power 23 per mole. And when you are taking molecular weight, kindly remember the molecular weight also is to be taken in SI unit, which is kg per mole. So the unit should be very clear to everyone. Okay. Now if Maxwell's theory was considered, he assumed that the kinetic energy was only due to translation of the molecules. So based on that, when we write the translational kinetic energy of the ideal gas molecules at any given temperature, when we add all the speeds, all the kinetic energies, so we get the final result as half m total VRMS square. So this is not the total kinetic energy, it is a translational kinetic energy, half m total VRMS square. So m total VRMS square can be written as 3 PV. So we can convert this and write as 3/2 PV, or you can write it as 3/2 nRT. So this is also one form, very important. You should be remembering this thing. Apart from this, you have one more important point. When we have ideal gas, there is no intermolecular attraction, there is no potential energy. So whatever is the total internal energy, this is simply equals to the total kinetic energy. So internal energy is equals to total kinetic energy, and this is expressed in the form F/2 PV or F/2 nRT. PV can be written as nRT, so F/2 nRT. So potential energy is to be neglected. Now kinetic energy total here is translational plus rotation of the molecules will also have kinetic energy, and also we have vibrational kinetic energy, but this is at very high temperatures only. So if nothing is mentioned, don't take vibrational or neglect vibrational. So F here, when you write internal energy is Ke total, which is F by 2 nRT. So F here denotes degrees of freedom. So if you talk of degrees of freedom, F value is 3 for monoatomic, 5 for diatomic, 6 for polyatomic, diatomic, and also linear polyatomic. For example, carbon monoxide. If you talk of carbon dioxide, I'm very sorry for that. Linear polyatomic like carbon dioxide, so that is also behaving like diatomic only. Linear polyatomic carbon dioxide behaves like diatomic, so it will also have degrees of freedom 5. So these are at normal temperatures. Okay, and when we have high temperature, then at high temperature vibrational degrees of freedom, when we talk of vibrational degrees of freedom, if there are n modes of vibration, in each mode there will be 2 degrees of freedom, so we will say 2n. So, or let's give another name so that you don't get confused. X is number of modes of vibration. So if there are x modes of vibration, degrees of freedom of vibration will be 2x. And mono, dia, poly, normally we have 3, 5 and 6 at normal temperatures. I hope this is clear to all of you. So you can put those values accordingly. So these are for ideal gases. Now one more important thing over here, sometimes they ask you the expression for U in terms of CV. Now internal energy is also expressed as NCVT. We write it as F by 2 nRT, and it is also written as NCVT, where CV is the molar specific heat capacity at constant volume. So from here we get CV as FR by 2. So for ideal gases, CV will be taken as FR by 2. Please remember this. Now next thing, whatever laws you have like Boyle's law, Charles' law, Gay-Lussac's law, they are all derived from PV is equals to nRT, different conditions whichever are met, that accordingly you will write the laws. Remember, PV is equals to nRT can be expressed in one more form. Sometimes they ask in terms of density. So from here, volume, as I said, is mass by density. So, and N is mass by molecular mass. So you can remember this important result. Rho is pressure into molecular weight upon RT. So sometimes questions are asked based on this also. So this is to be remembered. Clear? One more thing. We have one value which is called as mean square of speeds, VMS, mean square of speeds. So mean square of speed is nothing but VRMS square, right? General definition for VRMS, whenever we have a group of gas molecules, so VRMS is taken as the mean of the squares of the speeds. So VMS is VRMS square. So you can see V1 square plus V2 square plus Vn square by n to the power 1 by 2 is VRMS, right? For Maxwellian ideal gases, this value comes as root 3 RT by m. It is not always root 3 RT by molecular weight. It is only for those gases which obey Maxwell's law of kinetic theory of gases, right? Otherwise, in general, the method of finding VRMS is, if the speeds are known, you will use this. And when you take the square of VRMS, we call it as mean square. Now, gas molecules can move along all three directions, x, y and z axis. So when we take the mean square of x components of the velocities, when we take the mean square of y components of the velocities, and when we take mean square of the z component of velocity, so then these three values are seen to be equal based on pressure being same in all directions, we get this important result. And this value is simply 1/3 of mean square speed. So for Maxwellian gases, when we say Maxwellian gases Vrms is √3 RT by molecular weight, so it can be written as 3 RT by molecular weight. So when they are asking the mean square of x component, y component or z component, these are written as RT by molecular weight or kBt by mass of one molecule. So kindly remember this important result. So Vms is the mean square of speeds, whereas Vms x, Vms y, Vms z, these are called as the mean square of x components, y components and z components of the velocities. Okay. Apart from this, other molecular speeds we have average speed. When we are saying average speed, when we write V1 plus V2 and so on, the speeds by n, and this value is equals to, for Maxwellian gases only, not for every gas, for Maxwellian gas this expression comes as √8 RT by molecular weight. And one more speed is called as VMPS, most probable speed. The probability of finding such molecules is maximum which are moving with this speed. So that's why it is called as most probable speed. So this value is √2 RT by molecular weight. So for ideal Maxwellian gases which obey Maxwell's theory, then average is √8 RT by molecular weight, MPS is √2 RT by molecular weight, and RMS speed is √3 RT by molecular weight. So these are to be remembered. I hope these points are clear to everyone. Now let's move to next, that is law of thermodynamics. When we use the first law of thermodynamics, always remember it is based on conservation of energy and it is applicable to all solids, liquids and gases, real, ideal, everywhere. Everywhere it is applicable. But in this chapter we have to focus mainly on ideal gases. First law of thermodynamics, we say delta Q is equals to delta U plus work done overall, and when we take a small heat supply or heat exchange, then we reuse dQ, du and dw, right? So delta Q is delta U plus work done. Now this delta Q, delta U and W, in two important cases you have to remember its usage. Two important cases. First, if heat supply changes state of a system, state or phase, like solid to liquid or gas, etc. Example, water is getting converted to steam at 100 degrees Celsius. So in this case, temperature will remain constant. So what students do a mistake, they take delta U, sir, delta U will be to 0. No, steam at 100 degrees Celsius. Here what we have to see, water is converted to steam. So when there is a change in phase, the pressure equals the external pressure, which is taken as the atmospheric pressure. So pressure is equals to external pressure, which is equals to atmospheric pressure, and which is taken as constant. So in that case, if they ask you delta U of the system, you will write delta Q minus work done by the system. Delta Q is mass into latent heat. Here we are taking water to steam, so latent heat of vaporization. Now here work done, pressure multiplied by change in volume. Final volume you are getting steam, initially we had water, and P here is equals to P ATM. So from here you will get the change in internal energy. If it is coming positive, means internal energy is increasing. If negative, internal energy is decreasing. So remember this very important case. So when we have change in phase or state, that time you will use in this way the change in internal energy. Don't use NCB delta T or F by 2 NR delta T. Second case comes for ideal gases during a particular thermodynamic process of heat exchange. So suppose delta Q, that is heat exchange, is through a given process. So in that process we consider that process, general process, PV to the power x is equals to constant. This process we give a name, we call it as polytropic process. It is called as a polytropic process, and x is called as polytropic index or polytropic constant. So when you use in this particular case, so remember when we write delta Q is equals to delta U plus W, now here you will use fixed formula, delta U is NCV delta T, or better to use, as I told, F by 2 NR delta T. Work done for gases in such case, the process will be mentioned to you, P as a function of volume will be known, P will be given as a function of volume, and from here you will integrate from Vi to Vf. If it is isochoric process, pressure is constant, if it is isobaric process, isobaric process, pressure is constant, it will come outside, then you will get P delta V. But if we have other processes, you have to integrate. In case of isochoric where volume is constant, dV will be 0, so work done will also come out as 0. So in general, this value will change from process to process, so it is a path function. Delta Q will also change from process to process. We express it in the form of number of moles into C of the process, average C of the process into delta T. So this is called as average molar specific heat capacity of the process for the ideal gas. This thing should be remembered. Clear? So when we have this particular equation, you can see all the terms. Now we have two important values of C, one is called as Cp, one is called as Cv. So Cp minus Cv, these are molar specific heat capacities, this is always equals to R. Cp minus Cv is always equals to R. But if you write specific heat capacities, which is Cp by molecular weight, so this will become R by molecular weight. If you are writing molar specific heat capacity, you will use Cp minus Cv is R. But if you are writing specific heat capacity, then you have to divide R by molecular weight. So this is known as Mayer's relation, molar specific heat at constant pressure, molar specific heat at constant volume. Okay. So these are the three expressions. Now the molar specific heat of any general process, how to find that? If the process is PV to the power x is constant, first we find work done by integration, and then if we know delta U is NCV delta T, we can find the value of C average. Let's quickly see important relations. So when we have PV to the power x is constant, so what all important things you have to keep in mind? First thing, if the value of x is 1, if x is 1, then this process simply becomes isothermal. If it is isothermal, in that case delta U will become 0, delta Q will become equals to work done, which will be obtained by integration PdV. There the expression of integration comes in the form of log, because dx by x form comes, which gives you log, nRT log final volume by initial volume. This is what we use for isothermal process. Rest, if x is not equal to 1, general polytropic process, when x is not equals to 1, then in that case what happens? Work done when you integrate and find for a general polytropic process, it comes of the form PIVI minus PFVF by x minus 1. But we know PV is equals to nRT, so PIVI minus PFVF will become minus nR delta T by x minus 1, minus nR delta T by x minus 1. When we write delta U, it is fixed, it is NCV delta T, right? Now Cv can be written in one more form, Cp minus Cv I said is R, and Cp by Cv is equals to gamma, Cp by Cv is equals to gamma. So from there Cv can also be expressed as R by gamma minus 1. So you can express delta U in general as NR delta T by gamma minus 1 also. There is one more formula. Gamma, what is gamma? I said Cp by Cv, and this can be remembered. Many times students get a lot of confusion or they struggle to remember. You can directly remember gamma as F plus 2 by F. F plus 2 by F. Degrees of freedom plus 2 by F. This is a simple way of remembering the value of gamma. So delta U is this. So when we add both, you get delta Q. So delta Q, when we add, so the C value of the process, polytropic process, this comes as R into 1 by gamma minus 1 minus 1 by x minus 1. Very, very important formula. When you add work done and delta U, you will get delta Q, and delta Q is NC delta T. So from there, delta T cancels, we get this expression. But this expression is when x is not equals to 1. If x is equals to 1, it is isothermal process. This is what we say. If x is equals to gamma, we call it as adiabatic process. So just I am writing quickly, x gamma, it will be adiabatic process. If x is equals to 0, pressure will become constant. This means it will be isobaric. If x tends to infinity, then volume will become constant. It will become isochoric. You can put the conditions over here. You can get all the values easily. Very, very important formula. Okay, we'll see questions on all this. This is to be remembered. Apart from this, for PV to the power x is equals to constant, other values which you have to remember, they ask you slope of PV curve. When you write the slope of PV curve, slope is dy by dx, so dp by dv. So when you differentiate that form, it comes or transforms into minus x times p by v. Minus x times p by v. Now remember, greater the value of x, so slope will be more, that is steeper is the curve. The curve will become more steep, means it will be inclined more towards vertical. Up vertical or down vertical, it will be more inclined towards vertical, which has greater value of x. For example, isothermal, x is 1 and adiabatic, x is gamma. Gamma, remember, is always greater than 1. Gamma is always greater than 1. You can check with the values of f. Okay, 5 by 3, 7 by 5 and so on. So isothermal curve and adiabatic curve, which one will be steeper, which has more x? More x is for adiabatic. So adiabatic PV curve is steeper than isothermal PV curve. Very, very important condition. Slope. Next thing they ask, bulk modulus. Bulk modulus or 1 by C. C is called compressibility. Bulk modulus is 1 by compressibility. In elasticity chapter we study, bulk modulus is defined as minus dP by dV by V. So when you rearrange the terms, you will see here this comes as x times P. So polytropic bulk modulus for ideal gas is x times the pressure. So if pressure is known, just multiply it by the polytropic constant, you will get bulk modulus. I hope it is clear. Sometimes they will also ask you volume expansivity, which we have seen in thermal expansion. So volume expansivity, that is not adiabatic constant. We are denoting it as gamma V. Gamma V is dV by V dt. So if PV is given, you just differentiate it. If PV is given, you can PV to the power x is constant. What you will do, just substitute P as nRT by V. So from here we get a relation between T and V, and when you differentiate, so we will get the value of dV by V dt. When you use the multiplication rule of differentiation, you will get the value of dV by V dt as minus 1 by x minus 1t. So this value you can substitute directly from here. Okay. So this is some important, these are some important points that we have to keep in mind. Now, apart from this, what you have to keep in mind is, when I said work done in a process is integral PdV Vi to Vf, this is also equals to area under PV curve. So if volume increases, in a single process. If volume increases, work done positive. Expansion, work done positive. Volume decreases in a single process, work done negative. If there are multiple processes, you will add all those work done accordingly. Okay, so work done will come negative. If you have a cyclic process, in cyclic process, work done is area inside the cycle. Magnitude of work done is simply equals to area inside the cycle. And which cycle? PV cycle. And work done by the gas in cyclic process will be positive if PV cycle is clockwise. Sometimes they will give you VP cycle. VP is opposite of PV. So VP cycle if they give, so it should be anti-clockwise. PV cycle, it should be clockwise. And work done cyclic process will be negative if PV cycle is anti-clockwise, because in that case compressional work done will be more than expansion work done. So PV cycle anti-clockwise or VP cycle will become clockwise. Then you will get work done in cyclic process as negative. And when you write delta Q in a cyclic process, total work done and this value are equal. Why? Because when it is a cyclic process, you are returning back to the same state. So delta U is 0. So delta Q is equals to work done in cyclic process. Apart from this, one more important thing, whenever you see they have given mixture of ideal gases at thermal equilibrium and in a closed vessel, all the gases have the same volume, same temperature. In that case, what all things you should remember? First of all, when we write the total internal energy, you will take the sum total of all the internal energies. Next thing, when they are asking you total pressure, Dalton's law, sum total of individual pressures. But we know that pressure is nRT by V, so everything is same, only the moles can be different. Sum of all moles into RT by V. This is total pressure. Okay. Apart from that, they will ask you Cp, Cv, gamma, degrees of freedom of the mixture. Very simple. Cv of the mixture, when you use the internal energy formula, it comes as N1 Cv1, N2 Cv2 plus so on divided by total number of moles. If you remember in thermal properties of matter, last lecture, we had discussed that and I told there that we will discuss that part in thermodynamics. This is that part. Cv mixture is known. Similarly, when sometimes they will ask you specific heat capacity of the mixture, you will use N1 will become M1 mass, M1 SV1 or S1 plus M2 S2 plus M3 S3 and so on by M1 plus M2 plus M3 and so on. That will be specific heat. Here it is molar specific heat capacity, Cv mixture. Once you find Cv mixture, monoatomic, diatomic, I already told Cv is Fr by 2, you can quickly find that Cv mixture. If you know this, so Cv mixture can also be written as F mixture into R by 2. Clear? And from there you can find F mixture. Gamma mixture can be written as F mixture plus 2 by F mixture. If they ask you Cp mixture, nothing to do, just Cv mixture plus R, because Cp minus Cv is R, so Cp mixture is Cv mixture plus R. Sometimes they will ask you molecular weight of the mixture. So molecular weight, especially for RMS speed for a mixture of gases. So they are root 3 RT by molecular weight. So molecular weight of the mixture, same formula, N1 molecular weight of first gas, N2 molecular weight of second gas and so on divided by total number of moles. So by conservation of mass we get this formula for molecular weight of mixture. So these are some essential formulas or results which we have to keep in mind, right? So different processes are there. Let's see some questions based on whatever we just discussed. So okay, so our first question we are having over here, you can see that a gas is filled in the cylinder as shown. The two pistons are joined by a string. If the gas is heated, the pistons will. What will happen to the pistons? Now when the gas is heated, so heated means pressure will increase. So if pressure increases, so it will exert force on both the walls. So here also there will be force on the left piston and also on the right piston. Now if you see force on the left piston FL and force on the right piston, so what you will see, FL is equals to pressure into area of the left piston, and right piston will be pressure into area of the right piston. Now which area you are seeing is more? Area of the right side piston is more than left. So this value is greater than force on the left piston. So net force will be towards right side. So pistons will move in which direction? Towards right. Understood? I hope this is clear to all of you. Next question. 16 gram oxygen, 14 gram nitrogen and 11 gram of carbon dioxide. Okay, 3 gases are mixed and enclosure of volume 5 liter, temperature 27 degrees Celsius, pressure exerted by the mixture. We just saw. So what we can say, pressure exerted by the mixture is simply N total of the mixture RT by molecular weight. Now all the values are known to us. I'm sorry, not molecular weight. So here total pressure of the mixture N total RT by V volume. Now in SI unit 5 liter means 5 into 10 to the power minus 3 meter cube. R value I told, take it as 25 by 3. Temperature is 27 degrees Celsius, which you can keep as 300. N total number of moles. Oxygen you can see number of moles will be how much? 16 grams, so 16 by 32 for oxygen. Then we have 14 gram nitrogen, so 14 by 28 is for nitrogen. And then we have carbon dioxide, they have given 11 grams. So 11 grams divided by 44, right? So from here you will get the value of P mixture easily. So you can see 1 by 2, 1 by 2 and this is 1 by 4, right? So 5 by 4 moles we have, 5 will also cancel, that 3 and 300 will also cancel. Very simply you can get the answer for this, okay? Next question. Next question we are having, sample of ideal gas is taken through a cycle as shown. Okay, we have a cyclic process ABCA and it absorbs 50 joule of energy during the process AB. So in the process AB they have given 50 joule absorbed, and what else they have said, no heat rejected during BC, reject 70 joules during CA, 40 joule of work done on the gas during BC. Internal energy of gas at A is given as 1500 joule. The internal energy at C is being asked. So if you see the processes, they have given from C to A. During C to A, work is done on the gas. Now during the process AB, we have 50 joule. So delta QAB is delta UAB plus work done. Now in AB they have given 50 joule is absorbed. Whenever absorbed heat is there, you will use plus sign. Now what they are saying, no heat is rejected during BC and reject 70 joule during CA. Okay. Delta Q BC will become equals to delta UBC plus work done in BC. Now they are saying that 40 joule of work is done on the gas. When you have work done on the gas means it will be negative. So on the gas is negative, how much? Minus 40 joule. They are saying no heat in this part, 0. So that means what is delta UBC? Delta UBC means UC minus UB. So you can say UC minus UB will be minus 40 goes that side and becomes 40 joule. This is our second equation. And here you can see delta UAB, UB minus UA. This was our first equation, right? In question, they have mentioned something. At A, the internal energy is 1500 joules. Now, they have given one more process, that is CA. In the process CA, and wait, one more thing you can see from here, A to B, the process, it is isochoric, volume constant. So work done in A to B is how much? 0, because A to B is which type of process? Isochoric, isochoric volume constant. So from here, from first equation we can see UB minus UA is given as 50 joule. This is our first equation, and UC minus UB is 40 joule. Now they are asking internal energy at C. What can we do? We can simply eliminate UB. How to eliminate UB? Just add 1 and 2. So if you add 1 and 2, UB cancels, you get UC minus UA will become 40 plus 50, which is 90 joules. Now they have given you the value of UA. What is the value of UA given? It is given as 1500. So they are asking us the value of UC. Take it on the other side, 1590 joules. So 1590 joule will be the internal energy at point C. So just arranging the terms properly and using the condition that work done in AB is 0. So we get whatever is desired. Okay. Next, PV graph for two gases are given as shown. Plot 1 and plot 2 should correspond respectively to which gas? Now one gas is, you can see helium, oxygen, they have also used argon, nitrogen and so on. Now we have just seen that steeper curve means greater value. When we are saying PV to the power X is constant, polytropic process, and they have given adiabatic. So for adiabatic, X will become equals to gamma. Now you have taken different types of gases. X is equals to gamma. Now steeper curve, greater X or greater gamma out of two gases if you want to compare. So greater gamma, steeper curve. Which is the steeper curve? Which is coming more towards vertical. You can see more towards vertical is 2. So therefore we can say gamma 2 greater than gamma 1. Now you know monoatomic gamma is 5/3, diatomic 7/5. So which one has more value of gamma? 5/3 is 1.67 and this is 1.4. Which is greater? Monoatomic. So therefore gas 2 will be monoatomic and gas 1 will be diatomic. Both cannot be dia, one has to be mono, one has to be dia. So which one is the monoatomic gas? So 2 will be monoatomic and 1 will be diatomic. So 1 and 2, you can see oxygen and helium. So which one is satisfying? B option. So 1 will be oxygen and 2 will be helium. So according to that, we can select the option. I hope it is clear. Next question. Okay, when an ideal monoatomic gas is heated at constant pressure, what is the fraction of heat energy supplied which increases the internal energy of the gas? Better directly you can use the fraction of energy supplied which is increasing the internal energy. Means they are asking delta U by delta Q simply. When the constant pressure means pressure is constant. So we know delta U formula is NCV delta T and at constant pressure C will become Cp. So Cp by Cv is gamma, so it is nothing but 1 by gamma. What type of gas they have given? Monoatomic. Monoatomic we know gamma is 5/3, so 1 by gamma will become how much? 3/5. So B option will come from here. Clear? Next question. Consider two containers A and B containing identical gases at the same pressure, volume and temperature. Okay. They have identical gas, everything same. Gas in container A is compressed to half of its original volume isothermally. So for gas A, isothermal process, PV is equals to constant. So volume you have made how much? Gas is compressed to half of its original volume. So V you have converted from V0 to V0 by 2. So obviously pressure will be doubled. PV is constant. So volume half. So pressure will become 2 P0 in case of A. Now let's see B. B we have PV to the power gamma is constant. Now in this case also gas is compressed but adiabatically. So P0 V0 power gamma, P0 final volume is V0 by 2 ka power gamma. So V0 gamma cancels. P final will become, in case B, it will become P0 2 to the power gamma. And this was the final pressure in case A. So they are asking final pressure in B by final pressure in A. So P0 and P0 will cancel. So you have got 2 to the power gamma by 2, which will become 2 to the power gamma minus 1. Clear? Next question. Relation between U, P and V are given for ideal gas. Then what type of gas is this? Beta, if you have this type of form, ideal gas, U is 2 plus 3 by 2 PV. That means even if PV is 0, U has some value. So in that case, you always go for change in internal energy, dU. So 2 will be constant, so 0. So dU will become 3 by 2. Now see PV. PV can be written as for ideal gas nRT. So nR will come as it is, T will become dt. Now you can compare and say, we know du is F by 2 nR dt. So from here, F will become as 3. So if F is 3, which type of gas it is? It is monoatomic gas. So we can say that the gas is monoatomic. I hope it is clear. Next, n moles of ideal diatomic gas in a cylinder at temperature T. Suppose on supplying heat to the gas, temperature remains constant, but n moles get dissociated into atoms. Okay, total you had capital N moles. Now out of that, small n number of moles have dissociated into atoms, means they became monoatomic from diatomic. So heat supplied. Now in first look, what students commit a mistake, they think that okay, first thing though we have seen over here that volume of gas, they have not said that the gas is fitted with any piston or something. So there is no scope of increasing or decreasing the volume. So volume of gas, which is equals to volume of cylinder, this is fixed. They have not mentioned any change in the volume. So this is fixed. So therefore work done will become 0. So what students commit a mistake, then they will say delta Q will become equals to delta U. Now they read this line that temperature is constant, so they think that the delta U will be 0. But a temperature constant does not mean that it is isothermal. It will be isothermal if the number of moles are not changing and temperature is constant. Both things should be there. But here you can see that moles are changing. Here the gas is getting dissociated into atoms. So what we will do in this case, we have to write U final minus U initial. Now what is U initial? Simply you had monoatomic gas. So you will write diatomic gas, I am sorry for that, F diatomic gas, number of moles, F by 2 nRT. So diatomic gas 5, this is the value. Now finally, U final, you have some diatomic gas left, number of moles of diatomic left, RT by 2, total internal energy to be added, and whatever monoatomic is formed into number of moles of monoatomic atoms into RT by 2. Now diatomic F we know is 5, monoatomic F we know is 3. Let's see. Suppose the gas was X2 when it dissociates, so 1 mole of X2 will give 2x moles. So how many moles of X2 has dissociated? Small n moles. So small n moles will give you how many? 2n moles. So finally we have 2n moles monoatoms, and how many will be left out of capital N? Small n have dissociated. So n minus n moles diatomic will be left. So you can substitute over here. So you can take common terms, RT by 2 as it is common, 5 n minus small n plus 3 moles of monoatomic is 2n. So how much will be left? Let's see. RT by 2, 5n minus 5 small n plus 6. So that will be plus n. So delta Q is U final minus U initial. So when you write U final minus U initial, you can see 5 n, 5 capital N, 5 capital N cancels. So you get simply nRT by 2, small nRT by 2. Which one will be the correct option? The second option will be the correct one. I hope this is clear to all of you. Okay. Let's move. 1 mole of an ideal monoatomic gas at temperature T0 is expanding according to a law. They have given the law. So I said whenever law is given, just apply polytropic process concept. So I can write P by V as PV to the power minus 1 is constant. So this means from here X is equals to minus 1. Now they are asking the final temperature, initial temperature, both are known, heat supplied. So we can find delta Q will be Nc of the polytropic process into delta T. What is delta T? 2 T0 minus T0. What is C of the polytropic process? R 1 by gamma minus 1 minus 1 by X minus 1. What is the value of X? We will say minus 1. What is the value of gamma? They have given monoatomic gas, so 5 by 3. So when you put 2 by 3, it will go up 3 by 2. And this will become plus 1 by 2. 3 by 2 plus 1 by 2 will become 2. So that is 2R. So number of moles are also given to us 1. So we get our answer from here 2R T0. So our answer will become 2R T0. Simple way we can solve it. Okay. So gamma for monoatomic gas and X value from polytropic process. Next, molar specific heat capacity in a process of diatomic gas if it does a work of Q by 4 when the heat of Q is supplied. They are asking C of the process, but here they have not given the process, they have given work done and heat. How to find? Again, let's see. We know delta Q is delta U plus work done, right? Now from here we know delta U, which type of gas it is? It is monoatomic. So monoatomic, no, I'm sorry, it is diatomic gas. Diatomic, so F by 2 means 5 by 2 nR delta T. Delta Q is given how much? It is given as Q. Work done is given to us in the question as Q by 4. Take on one side. So Q minus Q by 4, 3Q by 4 will become equals to 5 by 2 nR delta T. Now what is the value of Q? We know Q can be written as Nc of the process into delta T. So from here N cancels, delta T cancels, 2 cancels. So value of C becomes 2 5s are 10, R by 3 will get divided. So C is 10R by 3. Any option we have? Yes, C. Clear? Next question. Internal energy of the gas is given by U is equals to 2 PV. Okay, internal energy they have given in terms of PV, but we know PV is equals to nRT. So you will must read the lines and write expression. So PV is nRT, so you have 2 nRT. That's it. So when we have this thing, then they are saying it expands from V0 to 2V0 against a constant pressure P naught, the heat absorbed by the gas in the processes. Okay, they have given pressure is constant. So 2 nRT we have U. So delta U can be written as 2 nR delta T. But they have given pressure and volume. So nR delta T, can I write pressure is constant? So nR delta T can be written as P delta V, because pressure is constant. So P delta V will become nR delta T. So what is this? Pressure is given as P naught. What is the change in volume from V naught to 2 V naught? It became V naught. Now what is work done? Work done is P delta V, because it is isobaric process, constant pressure. So it will become P naught into V naught. So delta Q is delta U plus work done. So it will become 3 P naught V naught. I hope this is clear to all of you. Next, n moles of an ideal gas undergo a process in which the temperature changes with volume. Now they have given temperature and volume relation. So if they give T is equals to kV square, so try to write it in polytropic. Remember, polytropic process we have PV to the power x is equals to constant. And if you put P is equals to nRT by V, which I told earlier also, so this can also be written as TV to the power x minus 1. In two ways you can remember polytropic, PV to the power x or TV to the power x minus 1. They have given T and V, so we can write this form here. T, bring V on one side, TV to the power minus 2 is equals to constant. That means this minus 2 is x minus 1. So x minus 1 is minus 2. So from here x will become minus 1, goes that side 1. So it will become x is equals to minus 1. So once we get x is equals to minus 1, they are asking the value of work done. So I told you work done in two ways. Either write PIVI minus PFVF by x minus 1, or if temperature change is given, so minus nR delta T by x minus 1. Both forms I told you. Which one shall I use? They have given temperature change, so we use that thing. How many moles they have given? N moles minus nR. What is the number of change in temperature? T naught to 4 T naught. So it becomes 3 T naught. And what is x? Minus 1. So minus 1 minus 1 minus 2. So this becomes 3 nR T naught by 2. So third option we have. I hope it is clear. Next, an interesting question where we have seen pressure and volume both are given, they are changing, but you can see both are increasing. So in this diagram, something we can see in this process, the graph is going up, so pressure is increasing. Graph is going towards right, volume is also increasing. If volume is increasing, this means work done will be positive, first thing. Also, temperature, all the three state variables, let's see first. Temperature, T is equals to PV by nR. Now pressure and volume both are increasing, so temperature will increase. Okay. Now what they are asking in the question, this the information we had collected from the graph itself. Now they are saying the process we don't know. They are saying molar specific heat of this process is C. Then C has to be related with CV. Let me make some, I think, misprint over here. In first, second, third and fourth option, they have related C with CV. Whether it is 0, greater than CV, equal to CV, less than CV and all. So how we solve this question? Well, I told you for C you need to write the process. So delta Q we know is delta U plus work done. Now if I write delta Q, I told I will write it as NC delta T. Delta U we know is NCV delta T. Work done, I don't know the process, keep it like that only. We are interested in C. So can I write C is equals to divide N delta T both sides. So CV plus work done by N delta T. Right? Now comes the final part. Work done, is it 0? No, work done is not 0, not negative, it is positive. We already saw. You can see temperature is also increasing. If temperature is increasing, delta T is also positive and number of moles is also positive. So that means C is equals to CV plus some positive value. So that means C should definitely be greater than CV. So when you are adding some positive number with CV, then you are getting C. That means C is greater than CV. So which one will be the correct option for this? we will say C is greater than CV. I hope this is clear. Very important type of question, theoretical. Next, sometimes you will get graph based questions where they will give you one graph and they will ask you to draw any other graph. The concept, just remember PV is equals to nRT and try to identify what is happening to each state variable out of pressure, volume and temperature. Let's see fast. So here we can see the processes given. If you see in AB, what is happening in AB, or we can do over here itself, I think we'll save time. In AB, it is a straight line passing through origin. Straight line passing through origin means here pressure is directly proportional to temperature. Pressure directly proportional to temperature, that means volume constant. Volume will be constant, and volume is constant in AB. Which all processes are possible for this? And you can see pressure and temperature both are increasing. So pressure is increasing and volume is constant in AB. Pressure increasing, volume constant. It is correct here. Here also it is correct. This is wrong because here volume in AB is changing. Here also it is wrong. So any one out of A and B should be correct. Now let's see the next process. Next process, if we select over here, which is BC. What is happening in BC? Here what is constant? Pressure constant. In this process, pressure is constant, and what is happening to temperature? Pressure is constant, temperature is decreasing. So when pressure is constant, temperature will be directly proportional to volume. So we can say in B to C, temperature should be proportional to volume. So temperature we can see is going left side, decreasing. So volume should decrease. So in B to C, pressure constant, volume should decrease. B to C, pressure constant and volume should decrease. It is happening in both. Okay. Now come to last process, which is C to A. What is happening in C to A? C to A, what is constant? Temperature constant. Temperature is constant means PV is constant. It will be a rectangular hyperbola. So it should be rectangular hyperbola. So which one is the correct graph? Second one. Here though they have shown a straight line, so this one will be correct. I hope it is clear. Next question. Three particles have speeds. Okay, they have given speeds here. So I told in the beginning, if speeds are given, group of speeds are given, then how to find RMS and average, whatever they are asking. So this question, three particles have speeds given, which of the following statement is correct? RMS speed exceeds the mean speed by how much? Okay. RMS speed, Vrms, I told under root of V1 square plus V2 square plus V3 square by 3, because there are three speeds. So you will write 2u whole squared plus 10u whole squared plus next one is 11u whole squared upon 3. Now calculation part you can check by yourself, and average or mean speed we know is 2u plus 10u plus 11u. I'm sorry, why I'm putting root over here? It's just average 2u plus 10u plus 11u by 2. So you can compare and check. So this was our first question. Now second, one more question we have below. Okay. Next question we have, 5 particles have speeds given. They are asking average velocity. Acha, average velocity. They are not asking average speed. Average velocity is the vector sum of velocities, and this value will be 0. Why? Due to randomness. Due to randomness, we always take average velocity to be 0. Clear? So 1, 2, 3, 4, 5. And if logically if we see, the correct option should be cannot be calculated, because we have not been mentioned over here that these are ideal gas molecules or not. What if these have speeds in the same direction? Then the average velocity can be something else. If they are in different directions, we can calculate that. So due to randomness, if there is randomness in ideal gas, if they are ideal gas particles, then it will be 0. Otherwise, if nothing has been mentioned, any case can be possible, so cannot be calculated, should be the better option. Again I am telling this, cannot be calculated will be the better option. Next, certain mass of gas isothermal curves between P and V at temperatures T1 and T2 are given, then they have asked to compare. Whenever we have such processes where isothermal curves are given, so you should know that comparison wise PV is equals to nRT, so T will be proportional to the product of P and V. So here you are seeing two hyperbolas, rectangular hyperbolas, so we have to compare the product of P and V. How we can compare? Simply select any volume as per wish. Suppose I am taking any volume V0, any value. So for this particular V0, see the corresponding pressure. This is for gas 1 P1 and this is for gas 2. So if you take any volume, if you compare, P2 is always greater than P1. So you are seeing P2 is greater than P1 for any given volume. So we can see that the product PV for gas 2 is greater than PV for gas 1. So T2 will obviously be greater than T1. Understood? So T2 will be greater than T1. Next, heat energy absorbed by a system in going through a cyclic process shown in figure, and then next we have a semicircle. Okay, mind it. Whenever you are seeing that they are asking heat energy absorbed in cyclic process, heat energy absorbed will be equals to work done. So delta Q cyclic is equals to work done in cyclic process, and you can see that they have given VP graph, mind it, they have given VP graph. So I will write, I said if PV is there, clockwise cycle work done positive, and if VP is given anti-clockwise, VP cycle is positive. So here you can see VP graph they have given anti-clockwise, so you will write positive area inside VP cycle. Now what we are getting plus sign, understood? Next thing is what students commit a mistake. If this is shown as a circle, don't take it as a circle, treat it as an ellipse. Why? Because one side you have pressure, one side you have volume. So always treat it as an ellipse even if they give you a circle. And for ellipse, you know, this being A, this being B, semi-major and semi-minor. So area is pi AB. So here basically this is 2A, which is 30 minus 10, 20 kilopascal, and this is 2B, which is 30 minus 10, 20 liters. So from here we get B is equals to 10 liter and A is 10 kilopascal. Now as I said, it is VP graph and anti-clockwise, so it will be positive area. So we will write pi A B with proper units now. Pi A is given as 10 kilopascal, so 10 into 10 to the power 3 SI units. B is 10 liter, 1 liter is 10 to the power minus 3 meter cube. So it will come in joules. So from here 10 cube, 10 power minus cube gone, so 100 pi joules. So 10 square pi or 100 pi joule. This is the answer for first one. Now let's see the second question. Second question, you are seeing a semicircle given. Now semicircle, how to find the work done? Basically what we do, if a semicircle is given, you are seeing two parts. Expansion is also there and compression is also there. If you see the compression part, total area will give you work done and that will be negative, and expansion part, this will be the work done which will be positive. So one positive, one negative. So when you subtract, basically you will get this as the work done. So work done will be shaded area, but area is never negative, but work done it will be negative. Why? Because you can see this part indicates compression and this part you can see is expansion, and compression is more than expansion because its graph compression part is lying above expansion. This is the compression part, this is the expansion part. So work done will be negative of the shaded area. So minus, again treat it as a ellipse, treat it as ellipse. So minus pi AB by 2, half of area of ellipse. Now what is A and B? Again from the diagram, if you see, this is A, which is 2 minus 1, 1 liter, and this is 2B. So 2B, because it is half ellipse, so 2B is 3 minus 1, 2, so B is 1 atm. So we will substitute the value, which will be minus pi. A is 1 liter, 10 to the power minus 3. B is 1 atm, 1 atm is 10 to the power, acha, they are asking in terms of atm and liter only. So I'm sorry, we will not change. So we'll keep it like that only. Pi, A is 1 and B is also 1. So minus pi by 2 atm liter. So minus pi by 2 atm liter, this will be the answer. I hope it is clear. Next question we have, a cyclic process is shown again. Which of the following curve represents the same process? Because just like we have explained earlier, we will see they have given BC is isothermal. So for this process, this is isothermal process. Isothermal process, PV constant, so temperature is constant. So better write here. One by one quickly. We have first A to B. A to B, what is constant? Pressure constant. P is constant, and what is happening to volume? Volume is increasing. V is increasing. So pressure constant, volume will be proportional to temperature. So temperature will also increase. V is proportional to T. Straight line passing through origin. So P constant. Acha, they have asked PT graph, right? This is what we get. So P constant and temperature increasing. Which process we are seeing? P constant, temperature is increasing. In first, it is correct, and in fourth. So which are not possible? P constant and temperature is increasing. So this is not possible. This is not possible. Now next we have the process B to C. This is isothermal. Isothermal, pressure is inversely proportional to volume and temperature is constant. And what is happening to the volume? You can see volume is increasing, pressure is decreasing. Pressure is decreasing, volume is increasing. So pressure decreases and temperature is constant. B to C. Pressure decreases and temperature constant. You can see B to C, pressure decreases, temperature constant. Here pressure decreases, temperature constant. These two are correct till now. Then comes the third process, which is C to D. What we have in C to D? In C to D, you can see that the pressure is decreasing. So temperature will decrease. Why? Since volume is constant, pressure will be directly proportional to T. So volume constant, pressure and temperature both will decrease. So in C to D, pressure and temperature both will decrease and straight line passing through origin, which is that part, this one. So we will say this will be the first option, will be the correct option. Understood? Okay. Next question, we have PV graph given like this. It is a decreasing straight line. What has been asked in the question is, how is temperature getting affected? How is the temperature getting affected in this process when we go from 1 to 2 for ideal gas? So ideal gas, pressure and volume is given. Now understand here, temperature we know is PV by NR, product of PV. So here what you are seeing is pressure is decreasing, volume is increasing. So you cannot say what will happen to temperature directly. Understood? So what we have to do when you have such cases where it is a bit dicey or you cannot understand what is exactly happening, always write the equation because it will help you. How? This is a straight line. So straight line equation, you know y is equals to mx plus c. So if you use y is equals to mx plus c, m is the slope and c is the y-intercept. So here y-axis you are having pressure, slope decreasing, so slope is negative, so I will write minus a, x is volume and c is the y-intercept. Y-intercept, this graph will cut the y-axis positive above origin, so plus b. So where a and b I am taking as positive constants. So write like this. Once you write like this, so we can say pressure. Now we are asked about temperature. So P is equals to nRT by V. So you can write minus AV plus B. So from here, write temperature on one side, minus A by NR V squared plus B by NR into V. Now can you see it is a quadratic equation? So equation is quadratic in V, and whenever we have quadratic equation means graph will be parabola, and coefficient of V square you can see is minus A by NR is negative. So temperature versus volume graph, if you draw temperature on y-axis, volume on x-axis, it will be a down parabola. It will be a down parabola. Now what does down parabola means? It means that first temperature will increase, then it will reach a maximum T max. At this point dt by dv will become equals to 0. By differentiation you can get that exact value also, and then it will decrease. So that means temperature increases first and then decreases. Very important question, and if they ask you to find the maximum temperature, you can use dt by dv is equals to 0. By that you can get the volume, then you substitute here, you will get the value of T max. Okay, I think this is the last question. Okay, one last question again. Here there is a great chance of committing error which we have to avoid. PT graph straight line. So what students think are a PT graph straight line? Question is, how is volume getting affected for the gas? So what happens here? Students think, acha, straight line, so that means it will be volume constant. No, volume is not constant because it is not passing through origin. Can you see the graph is not passing through origin? Is it passing through origin? Answer is no. So again, when you don't know, so you will write the equation. You can write the equation y is equals to mx plus c again. So y axis you are having pressure. This line is going up, so slope will be positive. So slope is positive. This line is cutting the y-intercept. This is C. This is also positive. So we can write pressure as, suppose take it as A, x-axis T, C as B, where A and B are positive constants again. A and B are positive constants. Now comes the final thing. We have been asked about volume. P is equals to AT plus B. So I said we can substitute P is equals to nRT by V. So this is the use of nRT, PV equals to nRT. So you can write AT plus B. So from here we are interested in volume. Take volume on one side. Volume will become nRT by AT plus B. But there is a big problem. Numerator also T is there, denominator also T is there. So what we have to check is that try to bring T only on one side, eliminate from the other. How we can get that? We just divide T. If you divide by T, you will get NR. In denominator you will get A plus B by T. That's it. Now see what is happening here to T. As this graph you are seeing is going up, P is increasing. And what is happening to temperature? The graph is going right side, temperature is also increasing. So what is happening over here basically? So since temperature is increasing, so B by T will decrease. A plus B by T denominator, so denominator will also decrease. So B by T will decrease, so denominator will decrease. Numerator is constant, NR is constant. So if denominator is decreasing, so volume will increase. That means we can say volume at B will be greater than volume at A. So this is how volume gets affected. If it is now you can remember it. If it is VT volume expression, if PT graph is above origin, cutting intercept above origin, volume will increase. If it is passing through origin, volume will be constant. And if you have PT graph like this, see the pen, like this, y-intercept negative, then in that case opposite will happen, volume will decrease. Clear? Shortcut method you can remember. So that will be all for this lecture. I hope you get benefit from this and are able to solve any type of questions that are based on kinetic theory of gas and thermodynamics. Okay, thank you.